Today let's go over the PowerCore V3 design and see what components they're using. Oh yeah, we do have a Discord, feel free to join that. It's mostly just for gathering EDM related information. So, PowerCore V3. Let's start with the main overview schematic. I am warning you ahead of time, there's a lot of red herrings left in the design, a lot of vestigial schematics that just never got used, but it's still a good overview to start with the block diagram. Here we get like a rough overview of how it's supposed to work. You get the power input going into the power management module. From there it gets split into the high voltage module and the high current module. The entire high current module doesn't actually exist, but we'll get into that later. And from there it gets combined in the output stage, which basically recombines them and also does current measurement and communicates with the controller. And from there it gets put into the spark gap. So it's a pretty simple overall block structure. Let's get into some of more detail. So for example, let's look at the output stage a bit more, as I feel like that's one of the most important parts. It actually handles the pulse generation. Over here is where from the supposed buck converter, where the high current comes from, and here is the MOSFET responsible for making the current pulses. And on the other side over here we have the boost converter output with the high voltage and the MOSFET responsible for making the voltage pulses. This split design lets you have one power supply at a high voltage and another one doing the current limiting, and you first turn on this MOSFET until you get a spark, and then you turn on the other one, and using these diodes you do not get any backfeeding of the high voltage into the high current supply. Here we have a resistive divider that gives 10k to 1 mech roughly, so a 10 to 1 divider with a pretty high impedance, but we're talking about pretty high voltages, so that checks out. From here it goes out to, here's the actual spark gap. There's a diode in parallel with the spark gap, I am assuming as like a freewheeling diode, so that's pretty good. And then from the return path from the spark gap, it goes through this current sensor, which then reports the actual current, and you get that to the microcontroller. Here at the bottom we have another MOSFET, which from what I can tell just does like the master enable. I'm not entirely sure why it's needed, but it's good to have probably. This, from what I can tell, does not actually do any of the pulse forming. This is just like a secondary on-off switch. Here we also see the three gate drivers for the MOSFET, since we need to switch these at like very high speeds. So they all use this gate driver 3 times, which seems to be able to deliver up to like 5 amps. That's not gonna go through the gate resistance here, but still that's a lot better than anything we did with the passive gate drivers in the last videos. So yeah, this is what I would call the core of the machine, the actual pulse forming. And from there, if you basically just had this and had like a high voltage supply connected to this side and a current limited supply connected to this side, you would have your EDM machine. Now let's go into the boost converter. It's just a simple boost converter. I'm guessing it's probably just gonna be a reference implementation. Yeah, so this is a boost converter chip here. It looks like basically just a reference implementation. Some more capacitors here just for having some bulk capacitance to smooth out low frequency ripples with like low ESR, 160 microfarads, so quite a bit. A lot of this is just buffering out pulses. We will see a lot more bulk capacitance and filtering later. They really wanted to make sure to reduce their EMI and make sure everything runs pretty smoothly, so you'll see lots of capacitance basically everywhere. You have a digital potentiometer which feeds into the actual boost converter for the voltage adjustment. So here on the feedback pin, the output pin going through the voltage divider with the digital potentiometer, and that controls the set point of this, so you can control the voltage. And here is like the main switching MOSFET for the boost converter. So let's see, there's the inductor. So this just regular boost converter. Here just goes to the output voltage. It's 4 pins, since that's just the topology of it. It has pads and pogo pins at the bottom. So this is a boost converter module, pretty bog standard, nothing special. Let's just look at the main motherboard actually, the PCB. So this is a main PCB. Here is the Vago style connector getting the 48 volts in, and from here it goes into these pads going to spring contacts, and above here sits the power management module. The power management module basically just does inrush current limiting and overcurrent protection. We can look at its schematic of the module. It's basically just like built around this chip, which does a smart high side switch, inrush current, overcurrent, and stuff like that. It also has high filter on here, having some noise suppression, a lot of bulk capacitance, an inductor. This is basically the first pi filter. There's an actual module called the pi filter, so there's a secondary one. But this is the power management module, basically just making sure you don't get an overcurrent condition and reducing some noise. That gets mounted on top of here. It is connected to the Raspberry Pi microcontroller, which sits at the bottom through these pogo pins. The vSense is not connected, but the other ones are, giving the iSense, fault, enable, basic stuff like that. From there, it also goes over to here. These are the spring contacts for the boost converter module. The boost converter module sits here, and we just looked at the schematic. So this takes the 48 volts in and then outputs it from here to the output stage, which is all this here. That's basically the output stage. So we saw the buck converter, but we said it doesn't exist. That's because it would have probably gone here in the middle, but that has just been replaced with the so-called pi filter module. The pi filter module is, this is the pi filter module. You can see here's the actual pi filter, the inductor with the two very large electrolytic capacitors, a small discharge resistor there, self-discharge resistor for the large electrolytic cap. And from there we have some more input capacitance to the pi filter and a whole lot of output capacitance. This output capacitance is actually what does the current limiting in combination with this inductor. There is no actual buck converter, it's just shorting this out through the high current MOSFET and discharging these capacitors and limiting more current rushing in with this inductor. That's all the current limiting does. That's why it's not adjustable in any way, shape or form, and any references to a buck converter just vestigial. Which is a bit confusing, since they do have a full-on schematic of what the buck converter would have looked like. And this is like a full-on schematic having like this buck converter IC and everything, but I guess it was just scrapped in the schematic but left out of the final design. This threw me for a loop for quite some time, as I just couldn't find it anywhere, and here, but yeah, they confirmed it. This whole thing is just not actually there. Anyways, this covers most of it. The pi filter module sits here in the middle. You see these two cutouts for the large electrolytic caps. It gets its 48 volts from here and then outputs it here, and from there it goes pretty much directly into the MOSFETs for the output stage, which are... Okay, so we have the MOSFET for the high current section here, the two diodes in series, these two diodes here, and from there it goes to the spark gap, to this here, and this diode is freewheeling diode here. This is a high voltage switch. This is the one in series down here that just does the enabling. So here we have that, and I'm guessing on the bottom we're gonna have the actual gate drivers. Let's see, can we get a 3D view of this board? Here we see the three diodes, current switching MOSFET, the voltage switching MOSFET, the on-off switch, and at the bottom there we have the MOSFET drivers. High current, the enable, and current sensor is also at the bottom, and this should be the high voltage MOSFET driver. You see these pads without a 3D model. Those are gonna be the three MOSFET drivers. Yeah, and that's basically an overview. We can at a later point look into the data sheets of the MOSFETs and evaluate their speed, but they are a lot faster than the one we had in our design, so that makes sense why this design performs so much better.